Hello and welcome to another power system analysis class. We started this class with a quiz. I want to share this quiz with online students as well. I will post their quiz separately. That's the reason today's class is going to be a little shorter because this quiz took more than I expected. The quiz is that we have a per phase analysis example. We assume we have a three-phase balanced Y-connected generator with the phase voltage of VAN of 1.2 with a degree of 0 degree volts, which supplies a delta-connected load with a per phase impedance of negative J.8 ohms. It goes through a transmission line with an impedance of J.15 ohms per phase, and the load is also connected to a second balanced delta-connected generator with a voltage of 1.1 with a degree of 10 degree volts through another transmission line with an impedance of J.15 ohms. We assume the system is balanced. We want to find the load line-to-line voltage, the line current supplied by each generator, the total complex power supplied by each generator, S, Y, and delta, and the total complex power absorbed by the load. It's similar to the example that we had last week. I'm going to post the solution online for you. And for the online students, you're going to have another quiz the same. And I would grade your quiz and I will return it next week. I've already graded your previous home quizzes. I think I returned some of them. But I would give you back all of them this week. And I'll post the solutions as well. So this week, we're going to start with power system operations, how a power system, distribution system, and the transmission works, the software behind it, how they manage the system manually and automatically. For those who work in Xcel Energy, you may be familiar with some of these. And also the laws behind these connections and the flow and direction of power and so on. So an overview of power system operations. The goal is to provide an intuitive feel for power system operations. Emphasis will be on the impact of the transmission system. It will be to introduce basic power flow concepts through small system examples. A basic power system, the basics of power systems. All power systems have three major components. We have the generation, load, and transmission/distribution. Obviously, as you know, the generation generates or creates electric power, the load consumes electric power, and the transmission distribution transmits electric power from generation to load. Lines and transformers operating at voltage above 100 kilovolts are usually called the transmission system. The transmission system is usually networked between, it could be different regions, states, even countries. The line transformers operating at voltages below 100 kilovolts are usually called the distribution systems or radials. So in the exam, if there was a question, what's the difference between a transmission system and a distribution system? It's the voltage, level of voltage, and it's different in different parts of the world. So this standard is for the US. It's in Europe, it's going to be different. Anything below 100 kilovolts is distribution system. Everything above that, it's going to be transmission. Transmission is for long distances. Distribution is within a region or a city that we usually have. This is a simulation of an Eastern interconnection, and you can see the transmission lines and the distribution lines color-coded in different colors. So the red, blue, they mean different levels of voltages. If I can find the color code, can't find it here, but you can see, let me see if I can find any. But red, for example, means it's a 300 kilovolt transmission. Blue means it's like a 70 kilovolt. So each of these are color coded, and the direction is shown, which shows the direction of the flow. It starts usually from a generator. You can see the generations, and then it ends at the distributions and the loads. Now, this is an example of a small power ward simulator case. As mentioned before, we showed the loads with arrows. Here we show it with green arrows. It indicates the amount of megawatts flow. So we have a load here. We use the circle as a symbol of generator. So we have one generator here in this bus and one load, simulated with one load. I have another bus over here. This is bus number 2, bus number 3, and bus number 1. This could be different regions or different, parts of a city. So you imagine bus number 2 is Amarillo, bus number 1 is Canyon, and they're connected to each other. Or different even parts. So this could be West Texas, this could be East Texas, for example, or Oklahoma and Texas. And these in the system, in the software, are used to control the output of generators. So you can see that with each generator, we have the ability to control the output of the generator as well. The direction of arrows is used to indicate the direction of the real power flow. And as we know, real power is measured by megawatts. And you can note that we have power balance at each bus. So you can see we have the amount of power that is going in and coming out is going to be equal. And if you add them, all of them, you're going to have an equal power on the bus. Imagine if this is a node, amount of current or power coming into the node and the amount of power going out of the node must be equal. This is the Kirchhoff's current law, the Kirchhoff law. So if I have 106 megawatts generated by this going through the bus, I have 14 megawatts, negative 14 megawatts here, and 20 megawatts. So we can see that we have to have a balanced system. If we have 20 megawatts coming in this direction, by the way, the arrows shows the direction as well. And this is bidirectional. It could go from one bus to another. It could go from bus 1 to bus 2 and bus 2 to bus 1. And you can see if you add all of them, it must be equal to 0. And I'll get back to that later in this class. So this is an example of a substation bus system, the one that I already mentioned. You already saw in that figure. And this is a three-phase transmission line. Now, we have some power balance constraints before we go back to that and explain that software simulator. So power flow refers to how the power is moving through the system. At all times in the simulation, the total power flowing into any bus must be 0. This is known as Kirchhoff's law, and it cannot be repealed or modified. Power is lost in the transmission system as well, because obviously we don't have an ideal transmission system. Some basic power control rules: opening or closing a circuit breaker causes the power flow to instantaneously change or nearly change, but usually it's a small, ripple delay. No other way to directly control power flow in a transmission line. By changing generation or load, or by switching other lines, we can indirectly change this flow. So if we have an overload in a system, the system nowadays it does automatically in a fraction of a second. But I mean, we have to be able to shut down a generator or direct, power to another load. Some systems have also these huge loads, which basically are huge resistors, and it's going to be like these huge heaters, I would say. If they have overgeneration, they would just dump the energy and create. But that's not for really huge, systems. Most of the time, we will cut back on the power on the generator. Now, you will cut the load. You would have scheduled shutdowns, blackouts that you're going to see. Same thing that happened in Texas in 2021. This demand is much more than the supply. The demand, the load. Yes, the voltage, frequency, all of that. You have to be careful to control both frequency and also voltage, the power that goes into the system. The thing is, most of the time we cut back the power, but it's not just the generator and load. I'm glad that you asked that. We cannot just increase both, like the generation and load as well. We have a limitation on the transmission line as well, and that limitation is determined by the resistance that we have in a transmission line. And the loss in that resistance is I square R. If you put too much pressure or high voltage, high current on a transmission line, what happens is first, the transmission line becomes very hot. When it becomes hot, what happens to metal? Expands, and we have the sagging of the lines. If it's too much, it's just going to simply melt. So we have some limitation. That's the reason they do tree, trimming, and there shouldn't be anything around it, because when it sags, and I gave you an example of the blackout of the 2005 blackout. First, the line starts sagging, then it will, contact the ground or a tree or something, and then it's a disaster. Okay. Now, this is a modeling consideration. Change is not really instantaneous, but it's pretty fast. The change isn't really instantaneous because of operation delays, which are near to the speed of light. There are also wave reflective issues, which we would address later. And you can see here the red one and the green one. The green one is the response rate, and you can see it takes a little bit of time. And if this is 60 hertz, this frequency, you can see it's less than one cycle till we catch up with the response. Now, the transmission lines also have some limits. As mentioned, power flow in transmission line is limited by heating consideration, losses, which are equal to I square R, can heat up the line, causing it to sag. Each line has a limit. Simulator does not allow you to continually exceed this limit. Many utilities use winter, summer limits as well. Now, another thing that we have to consider is that the limit that you have on a transmission line, imagine you have like a 10 millimeter thick wire in Houston, have the same wire in Amarillo, they have different limitations. Houston, we have higher humidity, higher temperature. When you have higher temperature, your limit is actually lower compared to the same line that you have in, Chicago or in Chicago or Toronto or something like that in Canada. So temperatures also vary in summer or winter. So the amount of load that you can put on a system in summer is different than what you can put in winter. Now, and it depends on the type of the wire, the material that it's made out of, thickness. It's a lot of different consideration. But when they are they're usually built in around a single standard. There is a table. I don't know, have you seen that table? But that table determines how much loss you have per thickness of a wire and so on. Now, this is an example of an overloaded transmission line. You can see that the transmission line is overloaded by about 29–30%. And you can see between bus 2 and bus 1, the amount of power that it's moving is going to be over 30% of the maximum that you can do it. For a few seconds, maybe this won't be a problem, but after a few minutes, it's going to have catastrophic, failure. That's the reason the system doesn't automatically cuts off the power, or it doesn't allow the generator actually to ramp up that much. But let's imagine a scenario that the load needs more power here, and the generator is able to actually provide more power. How can we transmit this power without overloading the transmission line? I'm sorry? More lines. Thank you. More lines, it's going to be a solution, but it's not going to be a quick solution. You need to have the infrastructure. It's going to be expensive. It takes a few years. If you are building a data center, yes, you can plan in advance. But imagine you have a very, hot summer. Everyone is turning on their HVAC, and it's a holiday. Everyone is at home, and you want to just simply crank up the power without any blackouts. What is the alternative way that companies can prevent that? That's a good question, but there's a limit on the amount of power that bus 2 can supply. So another way is actually to redirect energy. So instead of going through this transmission line, bus 2 can send the power to bus 3, and then bus 3 to bus 1. So you can redirect power. That's the reason we have like multiple transmission lines between states, so you can redirect power through another line. And that's one of the benefits of having these mesh networks in a power system. And again, you can see the direction of the arrow shows the direction of the power flow, and you see the load, the generator, and also the generators and the load and the bus itself. Now, in this particular case, this generator and bus 1 is actually acting as a load as well. You can see that the generator on the left is producing 502 megawatts. The generator on the right from bus 1 is actually consuming 194 megawatts. So that's going to be also a bit of a problem. Now, one important factor, as mentioned, is in the limitation is sagging. Therefore, we need to have the maintenance and on transmission lines. And one very important thing is trimming, and you've seen this a lot. And the reason that we trim these trees, and there is like a standard of it, is to prevent those accidents and blackouts from sagging. Now, a quick review or a reminder of the interconnected operation of different systems that we have: the Eastern interconnection, Western, and the Texas and Quebec. As mentioned, the power systems are interconnected across large distances. For example, we have most of North America east of the Rockies is one system, with most of Texas and Quebec being major exceptions. Individual utilities only own and operate a small portion of the system, which is referred to an operating area or an area. Transmission lines that join two areas are known as tie lines. This is important. The net power out of an area is the sum of the flow on its tie lines. The flow out of an area is equal to the total generation minus the total load minus total losses. This would be our tie flow. Now, as mentioned here, for example, if you add all of these again, you can see that we're going to have a tie line, and I'll give you an example on another one that it's not overloaded. Now, we have a area control error, or ACE. The area control error is the difference between the actual flow out of an area and the scheduled flow. There is also a frequency dependent component that we'll address later. Ideally, the ACE should always be 0 because the load is constantly changing. Each utility must constantly change its generation to chase the ACE. And that's different in different times of the day, the peak hours. And nowadays, these systems use, advanced machine learning AI techniques to actually predict as well. So if there's a, snowstorm or a heat wave, they would actually be able to start ramping up some of these generators. If it's a coal power plant, it takes a little bit of time to prepare and ramp them up. Now, this is the example of, oh, I forgot to mention this. Then we have automatic generation control, or AGC. Most of the utilities use automatic generation control to automatically change their generation to keep their ACE close to zero. Again, ACE is the amount of produced power compared to the load power, and you must be able to always match these. Usually the utility control center calculates ACE based upon tie line flows. Then AGC models sends control signals out to the generators every couple seconds. Now, this is an example of a 3-bus case on AGC. You can see that the generation is automatically changed to match changes in the load. So we have 266 megawatts coming in, 155 is generated. Now you have another 40 coming in to this load. And if you add all of these again, you can see that it will equal 0. And we want actually that to equal 0. And if we have this system here, you can see that the net tie flows is also close to 0. So we have 39 coming in here, but here you have 40 going out. So almost like a small difference between them. You have 12 megavolt reactive going inside here, and 11 megavolt reactive, consumed here. So you can see that there's a very small, negligible difference, and the difference is because of the losses in a transmission lines. You can see that the majority of the losses are in the reactive power. Do you know why? So here we have 25, 21, 11, 12. Why do we have more reactive loss here compared to this, or changes in reactive power, not reactive loss? So reactive power is mainly generated in transmission lines because these lines have inductance. And the longer the line is, you're going to have more reactive power difference in the systems. So this one is a pretty short line, we can say, but the longer the line gets, you get more difference between the reactive powers and the load and also the generation. Do you have any questions up to here? No? Little black square, red squares. Oh, these are the switches that we have, the switching systems and the control systems that we have, relays and controls that we have. And we can cut and control all of these, and the arrows shows the direction of the power flow. Oh, these are just, to indicate what these are. This shows like here the net flow is close to 0. And you can see it's 40 here, 8, 8. It's just, pointing to that direction. You mean these ones? This one? You mean these? These are just pointing. Okay, here? Okay, so when you have, this is a great question. This shows the load. So this black arrow shows the load. Green one shows the flow or the direction. So you have one load here. You can see that I have a black one over here as well. This is my second load, and I have third load over here. And loads, houses, factories, industries, things like that. Loads, actual loads, yes. Yes. Okay. Is it clear? Yes. Okay. So This is an example of what we call MISO real-time ACE. I don't know how many of you have seen these softwares, how many of you worked in substation transmissions in Excel? Oh, okay. I hope you could have a field trip and I can take you to one of these substations and see these softwares. Now, this is the Mid-Continent Independent System Operator. Previously, individual utilities did their own ACE calculations. Now we are part of a MISO, which does one for the region. So you can see that that system does it for a whole region. And this is a real-time ACE, which is available online with lots of other data. And you can see the online, control and control signals that you're going to have that controls the real-time, consumption and power generation and the control system. You can see going up and down indicates if now we have to generate more, consume more. So it's balancing it in real time. It's a very complicated system. Now, I think we don't have enough time to finish this. I'm just going to stop at this point. One thing to keep in mind is that the system and the software has made the frequency of blackouts less and less and the system more reliable. But now with the rise of smart grids and microgrids, there are a lot of challenges because you don't have control on those individual solar panels on the roofs. So now we are moving towards smart systems. But the problem with these smart systems, we have two-way connections. In these older systems, and this is like an older system, you only have mainly can control the generation. You have less control over the load. But in a two-way connection, you have control over both. But the problem is now you're connecting to a network. You're connecting basically on internet and makes you very vulnerable to cyber attacks. So imagine someone with a computer that could easily hack if they could, penetrate the system and, destroy a generator or load or something like that. But these systems are becoming much complicated right now. The older system, as I mentioned, it was a one-way system. You only had control over the generation, but now there's a lot of different factors that affect the system. Thank you so much. That's it for today. We are out of time. I would see you next week, and I will post a quiz for our online students as well. Thank you. Yes, I'll post that as well. Thank you for. Yes. Thank you.